Hello, I'm John Ellis, a hydrogeologist with Terra Incorporated, here to discuss the concept of critical head. In general, my hope for this recording is that everybody watching would come away with an understanding of what critical head is, how it fits into the bigger picture regarding subsidence, and also how it can be used as a tool when managing land subsidence. So the first part of this presentation will walk through what critical head is. Then I will show some worked examples using a combination of modeling and non-modeling techniques to estimate critical head. So the legislative intent of the Sustainable Groundwater Management Act, or SGMA, is to avoid or minimize subsidence. So given the intent is to avoid or minimize subsidence, one of the tools that can help accomplish this is the estimation of critical head in the aquifer system. So I want to talk a few minutes about the background on critical head, but in order to do that, I need to talk about the larger role of subsidence and how this plays into critical head. So here I will discuss the basic subsidence mechanics. So subsidence is based on the principle of effective stress. In an aquifer system, the stress from the overlying rock and water, the overburden, is balanced by the pore fluid pressure, which is the hydrostatic stress, and the intragranular stress, which is the effective stress. On the right side of the screen, you can see the diagram illustrating the overburden, which is the arrow pointing downward on the first column, balanced by the effective stress, and the hydrostatic stress, which are the arrows pointing upward. As the pore fluid pressure decreases, which is expressed here in this presentation as a groundwater level, the overburden stress increasingly transfers to the skeleton of the aquifer system, which leads to an increase in the effective stress. That increase in effective stress compresses the aquifer system skeleton, which results in subsidence. In the aquifer system, the subsidence occurs primarily in the clay beds because the clays are more compressible than the sand sediment and they drain more slowly when depressured. So in practical terms, what is happening here is that there is a pore fluid pressure gradient that forms between the clay beds and the surrounding sands in the aquifer. This gradient happens because once groundwater level declines begin, they happen much more quickly in the sands and much more slowly in the clay beds. So the pressure in the clays is higher than in the sands. Once this pore fluid pressure gradient begins to occur from the groundwater level declines themselves from pumping, water will begin to drain slowly from the clay beds and into the surrounding sands due to the pressure difference. As the water drains from the clay beds, the clay pore fluid pressure decreases, which increases the effective stress since the overburden stress remains the same. This results in the compaction of the clays manifested as subsidence at land surface. So with that said, when groundwater levels recover, the effective stress is reduced, which results in an expansion of the aquifer system skeleton and may result in a rebound of the land surface. An important point here is that subsidence continues until equilibrium is reestablished between the clay beds and the surrounding aquifer sand sediment. In natural undisturbed conditions, the pore fluid pressure, which is again here the groundwater level, is approximately in equilibrium. And that equilibrium has to be restored in order to stop subsidence. So the fastest way to restore equilibrium between the clay beds and the aquifer sediment is to have a rapid and prolonged rise in the aquifer groundwater level. As a final note, the time to equilibrate isn't the same in all areas of the aquifer. Thinner clay beds equilibrate faster than thicker clay beds, again because the time it takes for the pressure gradient to travel through a thick clay versus a thinner clay unit. So now we'll get into the mechanics of critical head. When it comes to subsidence, it's important to realize that the clays in an aquifer system have ingrained in them the memory of the past maximum effective stress, effectively the lowest groundwater level experienced in the system. This is the preconsolidation stress, which is usually expressed as a preconsolidation head in terms of a groundwater level. So preconsolidation head is generally used to define the initial maximum stress in the clay beds. When groundwater levels decline, this causes a decrease in the pressure in the clay beds, which increases the effective stress in these units and causes subsidence, as I mentioned earlier. Once these groundwater level declines exceed the preconsolidation head level, the preconsolidation head changes to a new lower value. That value is called the critical head. It's essentially the updated preconsolidation head once the preconsolidation head has been exceeded. On the right side of the slide, you can see an example of these dynamics. The figure shows the aquifer water level in blue, the critical head in the dashed red line, and the subsidence in the solid red line. You see that the groundwater level in the aquifer starts out higher and begins to decrease with time. It then exceeds the critical head and subsidence results. Because of the critical head exceedance, the critical head level decreases somewhat. Then the aquifer groundwater level recovers substantially, and you see a small amount of rebound in the land surface. This means that some of the subsidence that was experienced was elastic or reversible, but not all of it. Some of the compaction was permanent. And again, this is because the critical head level was exceeded. The extent and duration of the groundwater level decline below the critical head, along with the properties of the clays, determines the amount of inelastic or permanent subsidence that occurs. On this figure, you see the same thing happening 2 more times in succession, where the groundwater level declines below the critical head, resulting in subsidence and decreasing the critical head level. I want to point out, and I think you may have heard it before, but when dealing with subsidence, the lowest historical groundwater level is not the same as the critical head. The critical head, again, is in the clay units, not in the sand surrounding the clay units where most wells are completed. So the best way of determining the critical head is to either look at time periods when you're not getting subsidence or use an empirical approach to estimate it from a combination of groundwater level and subsidence data, or using modeling to determine the critical head. And again, the critical head level determines the type of subsidence that results. When you exceed the critical head, inelastic subsidence will result. And as before, raising groundwater levels quickly and for a long, prolonged period, particularly in basins that are experiencing ongoing subsidence, is the best way of decreasing the subsidence rate. So in talking about the critical head, it's also necessary to talk about the concept of residual subsidence. Residual subsidence is the continuation of subsidence after aquifer groundwater level declines have stopped because the water levels in the clay beds in the aquifer have not yet equilibrated. Subsidence will continue until that equilibration occurs, and in some areas where the critical head has been substantially exceeded for an extended period, residual subsidence can continue for many years. The figure on the right of the screen illustrates this point. The groundwater level decline below the critical head on the left side of the figure then recovers a bit, but the subsidence continues to occur for an extended period after the water level recovery. A few final points on residual subsidence. The best way to recover subsidence, to essentially to stop and manage subsidence and to get a recovery in some cases of groundwater levels, is to speed up the equilibration between the clay beds and the sands. The opposite approach would be if the groundwater level decline and it doesn't recover at all. So you have 2 opposite approaches here, one where the groundwater level recovers, and the second where the groundwater level stays at that depressed lower level. So in the latter situation, over a long enough period, the water level in the clay will decline down to the groundwater level in the aquifer. But this approach will result in the largest amount of subsidence, particularly if the aquifer water level declines have been rapid and prolonged. So you see this dynamic on the right side of the figure on this slide. You see a large amount of subsidence due to the rapid decline in groundwater levels, but the subsidence continues at a substantial rate for a long period after the groundwater level stops declining and stays constant. And to note, when the groundwater level decline has been substantial and prolonged, a groundwater level recovery above the critical head may be necessary to speed up the subsidence, to speed up the rate of equilibration between the clays and the sands and to slow that subsidence rate. So in terms of managing subsidence, Traditionally, what has been done is to use subsidence and groundwater level monitoring data to look at changes in subsidence rates. However, this approach is backwards looking and enacts subsidence management actions after the subsidence has already occurred. So using a critical head approach, you can define the groundwater conditions, specifically the groundwater level at which inelastic subsidence occurs. The estimated critical head provides a numerical, quantitative target for managing groundwater levels in the aquifer system. You can use the knowledge of the critical head to set sustainable management criteria. The critical head analysis allows you to connect water levels to inelastic subsidence in a robust way. It's really the linkage between the two. And by setting sub-basin minimum thresholds at or above the critical head, this provides the best chance of being protective of critical infrastructure. With that said, the traditional approach is suitable in certain conditions, such as areas without evidence of large rates of subsidence, or in areas not susceptible to large subsidence rates. These are areas where the conceptual model does not suggest the depositional environment includes thick layers of fine sediment that can undergo compaction, for example. So the critical head approach is necessary to identify when pumping would cause inelastic subsidence based on declines in aquifer groundwater levels. So in terms of estimating the critical head, there are non-modeling and modeling methods of doing this. So the non-modeling approaches include trend-based and empirical analyses methods. So looking at a trend-based method, this is the simplest analysis and uses general trends in groundwater levels and subsidence data to identify groundwater levels during periods of minimal to no subsidence. Subsidence is largely correlated with changes in groundwater levels. Therefore, the absence of subsidence during a sustained period of time indicates that groundwater levels are likely at or above the critical head, assuming the period when subsidence is minimal is fairly long. And you can see this method in a hypothetical figure on the right side of the screen. The black line is the subsidence and the blue line is the groundwater level. As shown on the figure, subsidence occurs during a period of groundwater level decline, but is minimized as groundwater levels recover during the subsequent period shown in gray. During the period where subsidence is minimal, groundwater levels generally increase or are stable. Selection of groundwater levels during this period, provided this period is more recent, may be reasonable for estimating critical heads and establishing subsidence SMCs that would likely be preventative of future inelastic subsidence. Now note that due to the approximate nature of this kind of analysis, groundwater levels and subsidence should be continued to be monitored and critical heads reevaluated as more data is collected. And it's most appropriate to use in areas where there has been both declines and recoveries in groundwater levels, and the subsidence has not been particularly large and there is not a substantial residual subsidence component. The second non-modeling critical head approach is to use an empirical analysis. This method uses an empirical relationship between groundwater levels and subsidence data to estimate critical head values. Estimates of critical head can be made using time series of displacement and groundwater level records. This empirical method identifies time periods where displacement is elastic, or again recoverable, and identifies the groundwater level during these periods. And there's two parts to this analysis. The first part is identifying time periods with sufficient rebound. An indicator of groundwater levels recovering above the critical head is generally the occurrence of land surface rebound, which demonstrates elastic subsidence. To determine the periods of rebound, the maximum subsidence for each time period needs to be established. This maximum subsidence is shown in the red line on part A of the figure on the screen. Then, the time periods associated with land surface rebound should be identified, shown as shaded gray areas on part B of this figure. The shaded areas on part B do not fully encompass the periods of land surface rebound due to the use of an uncertainty threshold, which is the purple line. Then the second piece of this analysis is identifying groundwater levels during rebound periods. So using the identified time periods of rebound, all groundwater levels during those periods are analyzed, and that is shown in part C on the screen. Ideally, groundwater level measurement should be relatively frequently, taken, so think monthly or better, to ensure that there are sufficient observations during the time of rebound. For each period of rebound, the lowest groundwater level, observed or interpolated, is recorded. A time series of the lowest groundwater level during periods of rebound can then be constructed, which is used as an estimation of the critical head, which is shown in Part D of this figure. The empirical analysis approach requires additional time and data to develop and interpret than the trend-based analysis. However, it provides a more quantitative estimate of critical head. And additionally, if a structured workflow is developed for the empirical analysis, it can be quickly implemented in multiple locations. So in order to estimate the critical head, you need to have a combination of subsidence and water level data. So this slide shows you the 2015 to 2024 water levels and subsidence in the Merced Subbasin at a site along Highway 99 that is circled for reference on the right side of the screen on the map. This data was obtained from the Sigma Data Viewer and the Water Data Library. The subsidence is shown in red on the left side of the screen, with the amount of subsidence on the secondary y-axis. And the water level altitude is in blue, with the altitude on the primary y-axis. You can see about 1.2 feet of subsidence over the 2015 to 2024 period, and the changes in groundwater levels in the upper and lower parts of the aquifer unit. Now, one of the questions when looking at subsidence in a subbasin is asking, how does the current subsidence compare to subsidence from earlier time periods? If you look at the site, again, there's about 1.2 feet of subsidence over a 10-year period, but how does that compare to previous periods? When you construct a long-term subsidence record using a combination of leveling and INSAR data, here you see the subsidence from 1901 through 2024 and water levels since about 1960. The current subsidence rate is in fact the greatest rate that subbasin has experienced at any point in time at this location. There's a total of about 2.5 feet of subsidence, but it's focused mostly on the more recent period. You can see a strong correlation between the subsidence rate and changes in the aquifer groundwater levels. So the longer record provides context for the current rates, and it helps when estimating the critical head in both modeling and non-modeling approaches. So I'll pan around the Central Valley at some other sites just to show a comparison of subsidence. So here I'm showing a site in the West Side Subbasin along the California Aqueduct. There's a bit of subsidence from 2015 to 2025, as much as 0.6 of a foot, although some of it was elastic, and it's currently showing about 0.4 of a foot of subsidence in 2025. So if you look at the big picture again and you plot long-term subsidence, you see something a bit different. There's been approximately 29 feet of subsidence at this site, but the vast majority of it occurred prior to about 1970. I'll note that this site is a mile away from the famous Joe Poland telephone pole photo in the top right corner of the slide. Historically, this area had the maximum subsidence rate in the state until the California Aqueduct began operations in the late 1960s, which resulted in a dramatic increase in groundwater levels and a substantial decrease in the subsidence rate. And you can see why there's a lot of subsidence early on based on these large groundwater level declines, and then a very large water level recovery with the advent of the surface water deliveries. Then starting around mid-2000s, water levels started to decline again in various years, particularly 2007 to 2010, 2012 to 2016, during cycles of drought, as well as 3 dry years in 2018, 2020, and 2021, where surface water deliveries were much lower than average. So you can see why you're starting to get some subsidence in the recent period, although knowing an estimation of what critical head is at this site would help this analysis, and I'll get to that shortly. I'm going to show one more site, this time in the Tule Subbasin in the southern Central Valley. There's been a lot of subsidence at this site between 2015 and 2025, right at about 5 feet, so an average of about 0.5 feet per year. One of the areas of maximum subsidence during the recent periods across the Central Valley is here in the Tule Subbasin. So again, if you look at the bigger picture and you plot the long-term subsidence, You see that this site has experienced a lot of subsidence across a long period of time, although the 2015 to 2021 subsidence rate of 0.6 of a foot per year is still greater than any historical period. So a lot of historical subsidence at this site, but also a lot of recent subsidence, although the rate has declined during the last few years. So I provide these comparisons for context when looking at subsidence and water level data from the recent period. Having this context helps with subsidence management, and understanding the subsidence and water level trends helps with estimating the critical head, whether using a modeling or a non-modeling approach. So here I'm going to talk briefly about estimating the critical head through a modeling approach. Here we're using the ModFlow code coupled with a skeletal storage, compaction, and subsidence package, which is also known as the CSUB package. So when using the CSUB package to model subsidence, you have to specify the number of layers and the compaction properties in each layer. This slide on the right shows a hypothetical example of a one-dimensional site to be modeled. There's 3 aquifer units in this example: the upper aquifer, the lower aquifer, and the Pliocene unit. You see that on the slide to the right in the text. To the right of this layering is a composition of the sediment at this site. The red color indicates intervals with clay sediment, known as interbeds. The tan color represents the sand intervals, and the yellow indicates a mix of sand and clay. At this site, there is a long history of groundwater level measurements and subsidence measurements based on a combination of leveling, extensometer, and INSAR data. It's best to model land subsidence using a code that simulates the delayed drainage from fine grain units, which again is the clay, into the surrounding aquifer, which is residual subsidence. Otherwise, if you don't simulate this residual subsidence, you may not capture the full extent of subsidence in future years, because subsidence is oftentimes not instantaneous, especially when there has been a substantial and prolonged decline in groundwater levels in the aquifer in the presence of compressible material. So for this example, it is assumed that groundwater levels are fairly consistent vertically across each of these model layers based on the available data, and that there isn't a substantial vertical gradient. Now, if that's not the case, then additional layers are recommended to be used when modeling each aquifer unit, again if there is sufficient data in the vicinity of the 1D site. One other item to consider when modeling land subsidence is how the fine-grained material is represented in the model. Now, using CSUB, you specify the number of interbeds and the thickness of these interbeds based on the lithology data available, plus clay properties such as the vertical hydraulic conductivity and inelastic and elastic specific storage. So these interbeds are specified as a system of delay beds representing more than one interbed, although you could specify a system for each individual interbed if you wanted. So it's best to try varying combinations of this setup, starting perhaps with an easier approach using a single system of delay interbeds to represent a combination of thick and thin clay beds, then increase the complexity if needed by using more systems of these interbeds. I say all of this because when modeling the critical head, the way you set up the CSUB package in your subsidence simulation can have a large effect on the critical head values you obtain. And if you use more than one system of interbeds, then you would want to look at the critical head values from each system of those interbeds, or perhaps average the critical head across the multiple systems of interbeds. So I'm going to show model critical head at 3 sites, but first I wanted to show the calibration results at these sites. So in order to accurately estimate critical head and to model it, we need to obtain a good match to observed subsidence and water level data at each site. In particular, the years where you see land surface rebound are important to focus the calibration on to ensure an optimal critical head estimation using these models. So this slide shows the calibration of the observed subsidence record across 100 years at these sites. So in the top right of the screen is the calibration to the site in the southern part of the Tule subbasin. The bottom right figure is the calibration at the west side subbasin that I showed earlier in the presentation. And the bottom left figure is the calibration at the middle Tule subbasin site that was also shown earlier in this presentation. So all this is to show that the calibration results will look good when you look at the observed versus the simulated data, which sets us up to talk about the simulated results, one of which is critical head. So here we're finally getting to the modeled critical head results. On the screen is the site in the southern part of the Tule subbasin. To orient you to what you see on this slide, the top pane on the right side of the screen, on that figure, it shows the observed water levels in blue and the subsidence in red. And these are the observed values at this site based on the long-term data analysis. On the top pane, you'll see two dashed lines. The one that looks like it tracks the subsidence is the modeled critical head. The bottom lighter blue dashed line on the top pane is the lowest historical groundwater level. The bottom pane of this figure shows you the difference between the critical head and the observed water level in the lower aquifer, although here that is technically the simulated water level. So if the observed water level is in green, it's above the critical head, and if it's in red, it is below the critical head. I'll note that I'm showing only the lower aquifer in this figure because the vast majority of subsidence in this location is from the lower aquifer based on nearby extensometer data. You'll see that early on there was a very large decline in the groundwater level, which is reflected in the red shading at the bottom. You'll recall that I mentioned how the critical head changes through time in response to groundwater level declines. You see that here at this site. Those rapid and sustained groundwater level declines in the aquifer rapidly depressurized the clays and resulted in the rapid declines in the critical head. Then, once the Frank-Kern Canal began water deliveries in 1951 and surface water supplies became available, the groundwater level rapidly recovered and for a prolonged period. So the rapid rise in groundwater levels quickly produced a lot of cushion above the critical head for many years due to, first, the rapid and sustained water level recovery in the aquifer, and second, because of how much the critical head had declined up to that point in time. So from about 1954 to about the mid-1990s, there was very little subsidence, and then even after, not much until about the mid-2000s, when water levels started to decline again after approaching or exceeding the critical head once more. This kind of critical head analysis can really help when you're telling the story of why you're getting subsidence in a particular location. So here's the critical head estimation for the middle Tule subbasin site. Again, I'll note that I'm showing only the lower aquifer in this figure because the vast majority of subsidence in this location is from the lower aquifer based on nearby extensometer data. So this site has had a lot of historical subsidence, particularly between 1940 and 1970, and then again between 2004 and present day. So you can see the critical head exceedances during those two periods on the figure in red. There's also been a lot of subsidence, though, even during the period between 1970 and 2004, when the lower aquifer water level was above the critical head. And this shows the continued residual subsidence that occurred during this period from the previous period of 1940 to 1970. There is a recovery of groundwater levels, but it's much less rapid and to a much lesser degree than the southern Tule site that I just showed you, which is why there's been a lot of residual subsidence at this site. And in present day, a large exceedance of the critical head since about 2010 has occurred. So here's the critical head estimation for the third site, which is the west side subbasin site. So here I'll show both the lower aquifer critical head estimate on this slide and the upper aquifer on the next slide, since both aquifers contribute to subsidence at this location. So for the lower aquifer, the critical head story here is similar to the southern Tule subbasin site. Early in time, there was a very rapid decrease in the lower aquifer groundwater level that resulted in about 1 foot of subsidence per year from the late 1940s to the late 1960s. Then, imported water from the California aqueduct resulted in a very rapid increase in lower aquifer groundwater levels that provided a cushion above the critical head for many years due to, again, number one, the rapid and sustained water level recovery in the aquifer, and number two, because of how much the critical head had declined up to that point. Then more recently, during periods of drought and limited surface water deliveries, the lower aquifer groundwater level decreased rapidly, causing some elastic subsidence and possibly some inelastic subsidence. I'll note here that the lower aquifer at this site is very thick, so the assumption that the water levels across the entire lower aquifer, that they're similar, it may not entirely hold, since this was modeled as a single layer, but I do think the critical head estimate is fairly accurate. So the story for the critical head in the upper aquifer is similar to the lower aquifer. Early time, it had some decreases, although much less than the lower aquifer, and more recently, it's had very rapid changes in the groundwater level, sometimes below the critical head. So the results are, in some cases, in the later periods, somewhat similar to the lower aquifer. So taken together, these critical head estimates do help explain the story of subsidence at each of these sites. And these simulations can also help with future subsidence estimates, given that any number of scenarios can be run on these models to project subsidence in relation to the critical head. So to summarize the critical head estimation methodologies, if a subbasin or area is experiencing a small amount of subsidence, the trend-based critical head analysis is probably appropriate. If an area has a larger amount of subsidence, the empirical critical head analysis is probably more appropriate. And finally, for an area with a large amount of subsidence, the modeling method is probably the best method in order to use to get estimates of the critical head. So to recap, my hope with this presentation is for everyone watching this recording to understand what critical head is and how it fits into the bigger picture regarding subsidence, and how it can be used as a tool when managing land subsidence. Thank you for your time, and I'm happy to answer questions at the email address on the bottom of the slide.